What is acceleration? Well, the definition of acceleration is the rate of change in velocity. So imagine you're in a Lamborghini. Here's our Lamborghini. And you turn on the engine, you blast forward. The feeling that you feel as you get pulled back into your chair, that is acceleration. So acceleration is the change in speed. The mathematical definition, or the formula for acceleration, is A with a bar over it. If you remember from last video, the bar is the standard symbol for average. So average acceleration is equal to change in velocity over change in time. You might notice this is very similar to the average velocity formula, which is delta x over delta time. But this time we're using velocity up here. So this is also v2 minus v1 over t2 minus t1. Since velocity is a vector, acceleration is also a vector. Now for instantaneous acceleration, which I'm not going to touch on today, because it's basically the same thing as instantaneous velocity. Instantaneous acceleration is A equals limit delta t approaching 0, delta v over delta t. So it's the same thing as up here, but you evaluate it in the limit of delta t approaching 0. Let's do our first example for today. You're driving your Lamborghini again, and it's down a straight road. You accelerate from 0 to 75 kilometers an hour in 5 seconds. What is the magnitude of the average acceleration? Let's use the formula. A equals change in velocity over change in time. The change in velocity is 75 minus 0. So 75 kilometers an hour divided by the change in time, which is simply 5 seconds. There's a problem. We have a unit mismatch. We have seconds, kilometers, and hours. So let's use a conversion factor to convert this up here into meters per second. We're going to multiply 75 kilometers an hour by two conversion factors. 1 hour over 3600 seconds to get rid of the hour, and 1000 meters divided by 1 kilometer so that we can cancel out the kilometer. Do your cancelling and you end up with 75 times 10 meters per 36 seconds. Put it into a calculator, you get roughly 20.83 meters per second. So why did I add this conversion step into this problem? Well, you're going to be doing this kind of thing quite often in future physics problems. And I'm just making sure that you get some exposure to it early on. We're going to substitute our new velocity into here. This comes out to 20.83 meters per second divided by 5 seconds. Do your calculating and you get 4.17 meters per second squared. This is your acceleration. And why is it squared? Here you see meters per second over seconds. Meters per second over seconds is equal to meters per second squared. So acceleration is always in meters per second squared. If you see second squared, it's accelerating. I'm going to give you an example to solve on your own. You have a sprinter, so sprinter running a race, and he accelerates to a speed of 9 meters per second in 1.38 seconds. What is the average acceleration in meters per second squared? Go ahead, pause the video, try to solve it. And let's solve this together now. A is delta V over delta T. The change in velocity is 9 meters per second, and the time is 1.38 seconds. This is roughly 6.52 meters per second squared. What about the opposite of acceleration? Deceleration. There's a common misconception that deceleration is always negative, but it's not always negative. And here's why. I'm going to draw a diagram to help you understand. Let's say you get our Lamborghini again, and he's moving to the left at a velocity of -5 meters per second. And the acceleration is going to the right. Well, this acceleration, because it's in the opposite direction of the velocity, it's counteracting the velocity and is therefore decelerating your Lamborghini. So even though the acceleration is going to the right, a positive direction, it's still decelerating your car because the acceleration and the velocity are in opposite directions. Here's the final example for today, and it's slightly different. Let's say you have a motorcycle and it's moving at 20 meters per second. It decelerates at a rate of 2 meters per second squared. So it's decelerating. The question is, how long does it take to come to a full stop? Well, this is going to take a little bit of rearranging. Let's take the formula for average acceleration. Delta V over delta T. If we multiply both sides by delta T, we get A T equals V. And then go ahead, divide both sides by velocity. We find that the time is equal to velocity over average acceleration. Now we can go ahead and solve for time. So T is equal to 20 from up here over 2, which is here. The time is equal to 10 seconds. So after 10 seconds of decelerating, the motorcycle comes to a complete stop.